Okay, so we can form these enolates or enols, and once we form them, that means that the carbonyl and the surrounding atoms are nucleophilic. We can add electrophiles to them. But what electrophiles can we add? What electrophiles have we added to other things before? Something that probably comes to mind is halogens. And it turns out that we can halogenate the alpha carbon of a carbonyl under various conditions. We'll see that we can do it both under acidic conditions and basic conditions. So how does it work? We're under acidic conditions, so that's going to promote that keto-enol tautomerization. And once we have the enol form, that pi bond, that is the CC pi bond of the enol, can add to the electrophilic halogen. So that's what's going to happen. So essentially we're going to promote that enol keto tautomerization with our acid catalyst here. We have acetic acid. And how does that work? Well, what's the most acidic or the most basic position on here? It's the oxygen. So essentially we can protonate that oxygen, which provides this species here, which is the first intermediate in our keto-enol tautomerization. Remember, this is just one of the resonance structures. We can pull the electrons up, which shows that we have a positive charge in that position. And then essentially, how do we get to that enol form? Well, that's just an elimination reaction, the same type of elimination reaction that we've learned about all the way back in first semester. So we have, and reinforced in chapter 11 and more chapters throughout this semester. But the acetate anion can actually come back at this point and allow for that enol to be formed. So at that point, we have our enol, and we have electrophiles around. One electrophile that would be around would be more of this acid. So it could theoretically protonate, and that would send it back through the equilibrium, because remember, this is an equilibrium. It's going back and forth, back and forth. If it grabs a proton, it's just going to go back. But another electrophile that's around is Cl2. So the other thing that can happen is that pi bond can add to Cl2, which breaks the Cl-Cl bond, forming the carbon-Cl bond and the positive charge right there. And at this point, a base could come along. So again, we'll just show it as the acetate anion. That would grab that. Those electrons would go to the oxygen, and that would go down to form that double bond to provide the product. So that's the mechanism of how we halogenate. We just start going through that keto-enol tautomerization, and this carbon is nucleophilic once it's the enol form, and it's going to add to any electrophiles that are around in solution. Is this going to happen just a single time, or could we essentially start back over from here? Like this could go to the enol, then we could add another equivalent of chlorine. Good question. Well, what we need to think about is the rate of the first chlorine that would be added versus each subsequent chlorine. And to do that, we're going to look at the species involved in this keto-enol tautomerization. So essentially, this protonation gives us this species here, which is the first species in that tautomerization, versus if we wanted to go through that equilibrium again, we would have this oxygen pick up a proton from there, and that would provide this species here. So the question that is in your course packet is, well, which of these species is less stable? Is this species less stable, or is that species less stable? Thought about it for a second, written something down. Yeah, so the less stable species is going to have the more the larger charge associated with it. Both of them have just a single positive charge, but which charge is more stable? And when we think about that, both of them theoretically are delocalized from the oxygen to the carbon, as we showed right here. But this chlorine, how is that impacting things? The chlorine's pulling electron density toward it. That's what chlorine does. It inductively withdraws. And as it pulls electron density away from that positive, it makes the positive more unstable. We don't want a larger positive, we want a smaller positive. So which cationic species is less stable? This one is less stable. So what does that mean? That means that the initial tautomerization reaction is going to go at a faster rate. So this tautomerization is going at a faster rate than subsequent tautomerization reactions. What that means is that the first halogenation is going to happen at a faster rate than any subsequent halogenation. Because of that, under these conditions, we can add a single halogen to the alpha carbon of these carbonyls. And there are some blanks on the course packet that describe this. You should check into that and write things in right now, and then come back. Okay, you've done that. It says, because blank is less stable than blank, etc., etc. What is there? Because B is less stable than A, so here's B right here, the acid-catalyzed halogenation of enols can effectively produce monohalogenated ketones. So if we want a single halogen on a ketone, we will use these conditions to do that. Right, so we can do acid-catalyzed or acid-promoted halogenation of ketones, but we can also do base-promoted halogenation of ketones. So how's this one going to work? Well, again, it's going to be you're doing the same type of enolate ketone equilibrium, and then once we have the electron density on that alpha carbon, that can grab the electrophile. So how is that going to look? Well, we have our base, we have the acidic proton right there, and we're just going to transfer the proton to that base. And again, this is an equilibrium. We would then have our alpha anion there that again is not just there, but it's also delocalized onto that oxygen. But essentially, this is now nucleophilic enough, it's an enolate, to add to the electrophile. So we have our Cl2 nearby, floating around in solution. If this runs into a water molecule first, it might grab the H from the water molecule, go back here, but essentially it's going to go back and forth in equilibrium until it bumps into the Cl electrophile. Once it does that, it will halogenate and produce the alpha chloroketone. And now we have to ask ourselves a question, right? Just like we asked about the acid-mediated halogenation, is this going to go at a faster rate once it's already chlorinated, or is it going to go at a slower rate? Well, what was the intermediate with the acid catalyzed that led to that enol-keto tautomerization? It was the protonated ketone. But that's not the same situation here. Here, the equilibrium is between the ketone and the enolate. So what would happen there? So we'd have more of that OH minus around that would grab the proton again and have an equilibrium of the enolate and the ketone. So again, we have to ask ourselves, it's all about rates, right? If the rate of this is faster than the rate of that, then we should be able to allow for monohalogenation. But if this rate is faster than this rate, then we wouldn't be able to stop the molecule from dihalogenating, putting multiple halogens on the same position. So to think about that, we have to ask ourselves, what about the stability of A versus B? And here we have A here, that enolate versus this enolate B. Which one of those two is more stable? So again, pause the video, ask yourselves that same question. Which is more stable, A or B? All right, you did that. You wrote something down about why it's more stable. B is actually more stable here because we have a negative charge on that intermediate, and the halogen stabilizes that through induction, right? It's pulling electron density away from that negative charge, and that makes it more stable. So B is the more stable species. So this equilibrium is actually going to be slower than this equilibrium. So what that means is that after a single chlorination, the next chlorination is going to happen at an even faster rate. So that would produce the dihalogenated product that looked like that. Where acid catalyzed halogenation of ketones, you can add a single halogen. Base catalyzed, that's not quite possible. And then again, in the course packet, I have a statement about that. It says because the monohalogenated enolate, in this case it's B, is underlined, more stable is what you would write in there. It forms faster after each subsequent halogenation. Therefore, monohalogenation under basic conditions is not possible. So that's where you're filling in these blanks down here. So we can halogenate under acid-mediated or base-mediated conditions, but they do different things specifically with the number of halogens that would be added to the molecule. So yeah. All right, so that brings us to a new reaction called the haloform reaction. So to start things off, what you really should do here is I want you to predict the product, and instead of writing it over here, I want you to predict the product down here of what we have written right there. So what is going to happen under these conditions? Okay, you already predicted that product. That's great. We have basic conditions. That's going to facilitate formation of that enolate. And we have iodine, another halogen in solution. So what's going to happen here? Well, we're going to form the enolate, and then that's going to add to the iodide molecule, putting an iodine in that alpha carbon position. This is a phenyl ring. I'll draw it out like I have it in the course notes. There is no hydrogen in this position, so we only have this side to add the halogens to. So essentially 3 times the last mechanism provides what I would hope you guys would be able to predict after that, Ci3. So this is where things change a little bit. So with 2 halogens on a carbon, things act a little bit differently than 3 halogens on a carbon. Essentially, halogens withdraw electron density. So what does that do? That makes them a good leaving group. So it turns out that when we have a good leaving group like this and we have base around, we have more OH minus around. OH minus, we've seen it add to a ketone, the carbonyl carbon, to make a hydrate. And in this case, it's going to look a lot like nucleophilic acyl substitution. We have a good leaving group here. And that base, instead of being able to deprotonate something, it can't anymore because there are no protons in those alpha positions. It's going to add to the carbonyl carbon, making our tetrahedral intermediate. And then that tetrahedral intermediate is going to come down, and it's going to kick out the best leaving group. In this case, once we have 3 halogens on that same carbon atom, it actually stabilizes the negative charge that would be on that carbon, making it into a good leaving group. So 2 halogens there, not a good enough leaving group. 3 halogens, now it's actually the best leaving group possibility. So that provides the transformation from that to a carboxylic acid and Ci3 minus. So Ci3 minus is pretty stable by itself, but once we have this carboxylic acid, we now have a strong acid in solution. So what's going to happen here? Well, if this is the most basic thing, if we have more OH minus around, that could act as a base, but also this can act as a base and just deprotonate that acidic proton to make the final product of this reaction a carboxylate plus HCI3. So haloform, why is it called that? Well, chloroform is CHCl3. Haloform is halogen, the same thing as chloroform. Essentially, we're forming chloroform or iodoform or bromoform, any of the halogens that would be part of that type of thing. So that's why it's called the haloform reaction. So how is this different than what we just saw with the base-mediated conditions and the secondary alpha carbons? Well, we need to have 3 hydrogens, this is a CH3, for us to put 3 halogens on there. And until we get the 3, it's not a good enough leaving group for this to occur. So this can actually be a test for, do we have a methyl ketone, essentially. So there's a blank here. The 3 blank make the carbon a good blank group. The 3 halogens make the carbon a good leaving group. And in that course packet, nucleophilic acyl substitution occurs as a result. So again, what have we learned so far? We learned that if we have a methyl ketone, we're going to go through this haloform reaction, 3 subsequent alpha halogenations followed by nucleophilic acyl substitution. If we don't have a methyl ketone, we're just going to put 2 halogens on that alpha position. And if we're under acidic conditions, that's the way that we can add a single halogen. So again, this is a figure from your textbook, but it shows all the different options. Acid gives us a single halogen on there. Base gives us as many halogens as there can be. With 2 hydrogens there, it can only do 2 halogens. 3 hydrogens here, it can do all 3 hydrogens, or 3 halogens. So those are all the possibilities for alpha halogenation of ketones and aldehydes.